Well, hello everyone, my name is Romain, I'm a paleontologist, I'm a specialist in dinosaur legs, and today I'm going to answer your questions about dinosaurs. Fasten your seatbelts. We have Juste de Citron asking us, where can you find dinosaur fossils in France? If you're like me, you might be surprised. I always thought there were no dinosaurs in France, but there are actually many dinosaur sites there. In fact, France, when you look at a geological map, is made up of several sedimentary basins. Basically, we have layers of rock that are deposited flat like this, with the oldest ones at the bottom, and then more and more recent ones on top. And then, with tectonic mechanisms, these layers will be uplifted, so we'll have older parts exposed on either side, and that's what is called a basin. We have several sedimentary basins in France that were deposited during the Mesozoic, some of which actually contain continental sediments that hold dinosaur fossils. Honestly, there are quite a lot of them. For example, I do a lot of excavations in Charente. There are several sites in Charente that contain dinosaur fossils, so already you can find plenty of them there. I was there in the spring at an Upper Cretaceous site in Hérault. Hérault as well is a region that is extremely rich in dinosaur fossils from that period. There are also sites in the Var, so those ones are not necessarily all active anymore, and you can even find some, I believe, in the Alps Maritimes. Really, there are a lot more than you might think. I grew up in Lorraine, for example, near Nancy, and in Lorraine, it's mostly marine sediments. Some continental sediments contain dinosaur fossils, which I only discovered after leaving the area. I was very frustrated. Jeff Gauthier asks us why there are so few so-called dinosaur insects, and so I understand why dinosaur is in quotation marks. It's true that this question brings up the idea of dinosaurs in the collective imagination. It's true that sometimes as scientists we get a little disconnected from that, so just as a reminder, dinosaurs are really a family of animals that is defined in a robust way. But it's true that sometimes I feel like this word is used in a more popular way, as if it just means fossils, and then more or less big animals with scales or not. But in this case, in this question, I feel like I'm being asked why there are so few fossilized insects instead. There you go, that was just to clarify, to make sure we understood each other. And as for so few insects, fossilized insects, well, I don't necessarily agree with that. I would say that insects are actually quite well represented. I mean, there are a lot of insect fossils. You see, insects are mostly made up of what's called an exoskeleton. It's an external armor made of keratin that usually preserves well as a fossil. In this case, we don't necessarily need exceptional deposits. We don't always need amber, for example, the most well-known example, to preserve insects. So it's not necessarily that rare. Still, it's true that every fossil is rare to begin with. It's something exceptional to fossilize an organism, and it's even more so when we're talking about an organism that lives on land. Quite simply because to make a fossil, we need water. We need an organism to fall into water and be covered by sediment so it can be preserved. So it's true that, relatively speaking, we're going to have a lot more fossils of marine organisms than of terrestrial organisms, for example. And so that's why dinosaur fossils are still relatively rare, because it's much more difficult to preserve them. And actually, that's the case for many terrestrial animals, continental ones, which include insects. So I think in that sense, indeed, you could say that it's a bit rarer to fossilize insects than, for example, fossil fish or marine microorganisms. But that being said, we still have a nice abundance of insect fossils. Chris Tinham asked us if the representation of dinosaurs we have today is reliable. I would tend to say yes. We're still moving toward a fairly good reliability in the representation of dinosaurs today. So the field of paleontology basically is based on a pretty important criterion. It's called comparative anatomy. So basically what we do is, from the dinosaur remains we find, mainly bones, we compare the morphology of those bones with that of modern animals that are the closest relatives. So it's going to be a lot of reptiles, but also birds. And in the end, we'll rely on all the common anatomical features to try to get the most accurate representation of dinosaurs possible. There's also, I think, something else to consider, which is the representativeness of a species. Basically, what percentage of a species' skeleton has been found. Obviously, the more bones we find for a species, the more accurate our representation will be. For example, suppose we have two species of dinosaurs that are very similar, and for one of them we have a lot of bones that have already been discovered, while for the other, some bones are missing. Since these species are very closely related, we can use what we know about one species to infer information about the other species that we know a little less about. Gradually, all this helps us build a more reliable physical representation of dinosaurs, though much remains to be discovered. So what I'm saying now is true, but in 2025 it might not be anymore. In 10 years we might realize we've made huge progress and that we were actually wrong about something, but that's how science works, of course. Christine Hawker is asking us why dinosaurs were so big. It's a bit difficult to explain why dinosaurs were so large. So dinosaurs, at least the non-avian ones, we'll come back to that later, lived between 230 and 66 million years ago. And so that's during the Mesozoic era, divided into the Triassic, Jurassic, and Cretaceous periods. I find it quite interesting to go back a bit into the history of science, where in biology there's actually a rule called Cope's rule. And basically this rule, which was widely applied in the past, says that it's standard for any species to increase in body mass over the course of their evolution. So since this rule was commonly accepted, let's say, it didn't necessarily prompt people to ask why dinosaurs, among others, became large. People just thought it was normal. And so people were more interested in what the limits of this rule were, meaning at what point you stop growing, for example. And actually, this Cope's rule was increasingly undermined by scientific research, which realized that it didn't really hold up in most cases, actually. And so people then started to wonder how dinosaurs became big. I think one of the first things that's most often brought up about why and how dinosaurs could become big is mainly the fact that their metabolism was different from what we might imagine. When they were discovered, actually, at the discovery of dinosaurs and the first scientific studies, they described animals that were cold-blooded ectothermic animals whose body temperature depends on the external environment. And we gradually realized that, in fact, these animals were actually endothermic. So actually, they generated their own body heat. And so that obviously suggests much higher metabolic rates and also growth rates that can be much greater. And so it's really by looking inside dinosaur fossils. There are some techniques that are slightly destructive. We make thin sections by hand, which we can then look at under the microscope. On many fossils, it's not even visible that they've been cut. And then we can also use other techniques like things borrowed from 3D imaging CT scans, basically like X-rays of bones. And these techniques actually allow us to look a bit at the growth of dinosaur bones. Basically, we have what we call growth arrest lines that are deposited in sections within the bone. It resembles what you'd see in a tree trunk. By counting these rings, we can determine a dinosaur's age. And also by looking at the thickness between each of these rings, as well as the nature of the bone tissues deposited between them, we're able to determine growth rates. And we realize that, for example, in sauropod dinosaurs, the growth rate in the youngest ones is extremely high. And when I say extremely high, I really mean a lot. A baby sauropod can grow by 2 tons per year, for example. So that's really huge. And that's much more, by the way, than a potential predator, since a large theropod, like a T-Rex, doesn't exceed a ton per year, which is already huge. It's around 500, 600 kilos, if I remember correctly. There you go. So all this to say that in these animals, there are internal factors that make them able to become big very quickly. And so obviously that encourages this. There are also certain species that have characteristics that have actually become specializations for a high body mass. And so some of these species already had these characteristics before later species, let's say, developed a high body mass. So that also made the evolution of gigantism a bit easier in some species. There can also be external factors that influence the size of animals. If I take the example of sauropods, in a family of sauropods that had already become giant, there is a group of species that developed what we call dwarfism. So here we're looking at an evolutionary reversal, really a return to a somewhat smaller, less gigantic size. This dwarfism, or size reduction, is interesting because it occurred in isolated species living on an island. And so this still suggests that living in a habitat with a bit less space, maybe a bit fewer resources, can also influence the selection mechanisms regarding the size of these animals. This is called insular dwarfism. In the past, there were hypotheses that had been proposed which had rather, let's say, simple answers, with, for example, this idea that was quite widespread that in the Jurassic, there were higher oxygen levels in the atmosphere, and this higher oxygen level would have allowed dinosaurs to evolve to much larger sizes. And in fact, it has been shown multiple times afterwards that these oxygen levels in the end were not higher during the Jurassic than they are in the atmosphere today, and so they wouldn't necessarily have favored, in any case, the increase in body mass. And even beyond that, there are studies that have shown that there isn't really a causal link either between higher oxygenation of the atmosphere and an increase in body mass. We have a question from Aurélien Louvet who asks us, to what extent did Jurassic Park mislead viewers and scientists? And there's also a little postscript asking, a gorilla against 100 people. Okay, but a T-Rex versus how many Deinonychus? There you go. Very interesting question. So in this case, Jurassic Park, it's true that personally, I think we tend to really use the debunking angle actually to show what Jurassic Park may have done wrong to the popular representation of dinosaurs and to scientific dynamics. But in reality, it's a movie, let's not forget, that came out 30 years ago and transformed the way people saw dinosaurs. It's true that everyone from my generation at least grew up in a world where we knew that birds are dinosaurs, for example. And I think that this knowledge was largely spread by Jurassic Park, as well as the idea that dinosaurs were dynamic, warm-blooded animals. So just for that, this movie didn't really mislead the audience. I think we need to be very clear about that. But it's also true that it's always interesting to see that the movie from the start already included things that were wrong, and that was intentional. For example, there's a dinosaur called the Dilophosaurus with a frill that unfolds behind its head and spits venom. I wish that dinosaur were real. The Dilophosaurus existed but lacked those features. Some traits were just hypotheses at the time and have since been disproven. And so that's typically the idea that the T-Rex's vision was based on movement. Don't try that if you ever find yourself face to face with a T-Rex, because that's not true. So there you go. In this case, it's understandable. This also brings up the T-Rex versus Deinonychus debate. There's also the use of the name Velociraptor for basically that big dinosaur you see in Jurassic Park. So the dromaeosaur that's about 2 meters tall and super dangerous. So in reality, they called this dinosaur a velociraptor, but even back then we already knew that Velociraptor was a small dinosaur weighing about 15 kilos, roughly the size of a goose. So we're nowhere near the representation the movie gave, but it's interesting that a dinosaur like Jurassic Park's Velociraptor actually existed. It was actually discovered around the same time as the book was written or the movie was released, I can't remember exactly, and this dinosaur is called a Utahraptor. So it's a dromaeosaur that was discovered in the state of Utah, as its name suggests, and in this case its size actually matches what we see in the movie. So a big dromaeosaur like that could weigh between 300 and 500 kilos. So really you can imagine a terrifying animal. And so that brings us to the question of one T-Rex versus how many Deinonychus. So Deinonychus is a slightly intermediate, let's say, in terms of size between a Velociraptor and a Utahraptor. I think the person meant to talk about Utahraptor in terms of size, the raptor from Jurassic Park. Well, listen, the movie showed us that 3 wasn't enough, but in my opinion, I'd say that 5 would be more than enough. 1 or 2 Utahraptors could create a distraction. And then, since apparently they would be organized hunters, they would know very well that attacking a femoral artery or something like that would unfortunately bring down the T-Rex. So that's my opinion on the matter anyway. We have Hippe Casimir, not verified, asking us how we can determine the color of dinosaurs, in parentheses, skin, feathers, and eyes. For the eyes, that's going to be complicated to begin with, because it's true that for dinosaurs, well, even for any fossilized organism in general, we don't necessarily preserve everything that is soft tissue. So those are structures other than bone structures like cartilage and skin. And as for fossilized eyes, I think as far as I know, they've never actually been found. So it would be a bit complicated to use any possible methods to infer the eye color of dinosaurs, unfortunately. On the other hand, when it comes to skin and feathers, it's quite rare, but there are indeed teams of paleontologists who have been able to make suggestions about the colors. So once again, it's very rare. We can't have a very precise idea of the colors in dinosaurs. On the other hand, what we do have is that in some dinosaurs, specifically from the theropod family, which is the family of all bipedal carnivorous dinosaurs like Tyrannosaurus rex, velociraptors, and so on. And so in this family, we have a part, quite a significant part of this family, that developed feathers. And so we are able to find fossilized feathers, which are often preserved all around the skeleton of certain animals. Birds are part of this family. And inside the feathers, we can observe what are called melanosome structures, which is interesting because what we know in nature today is that the shape of melanosomes is linked to certain colors. And so some scientific teams have been able to study the variety of shapes in these melanosomes in some of these feathered dinosaurs, and they found colors ranging from very intense black to really bright, vivid red, actually. In any case, this allows us to rigorously demonstrate that dinosaurs had color patterns that were not very gray or very discrete, as you can see, for example, on this dinosaur, where it was really the vision from the first Jurassic Park movies, for example, or even older views we used to have, seeing these animals as very reptilian, actually. You have to imagine something much closer to birds with really flashy colors, actually. Valu0012 is asking us, so here, again, it's a bit of a complicated question because we're really talking about something that doesn't necessarily get preserved as a fossil. Sound can't really be preserved. The organs that let us produce sounds are made of soft tissues. So typically it's the larynx in most vertebrates, but in birds we have the larynx. But we also have another organ called the syrinx, which has been found in some fossilized avian dinosaurs. So again, it's very rare. We can't really make inferences, but it's interesting. First, to try to reconstruct a bit of the evolution of sound production in dinosaurs, we're making progress little by little to see when the syrinx really evolved in this large family. It's really not clear yet for now, but I think it would be an interesting avenue to explore in order to move forward with reconstructions of the sounds that dinosaurs could potentially have made. So there is still this anatomical feature that is known in dinosaurs. We're going to look at a dinosaur also in the ornithischian family called Parasaurolophus. And so the Parasaurolophus is a dinosaur with a duckbill, which has a long crest on its head like this that goes backward. And actually this crest is hollow. It would be connected to the animal's nasal cavities, and it could potentially have been used to produce sounds, maybe to communicate with other members of its herd or something like that. So there are research teams who had fun trying to push air through this horn and trying to reconstruct the sound this animal might have made. So yeah, I can't really imitate it for you. We may already have at least one dinosaur sound that has been produced. And then, to go a bit further on this, you see, even though I've been telling you that we don't have direct evidence to make these inferences, we generally try to find indirect ways to move these questions forward. And so if we can't directly reproduce the sound a dinosaur made, maybe we can look into what a dinosaur could hear. And that can give us some clues about what sounds therefore certain dinosaurs could produce. It turns out that the ear of dinosaurs isn't necessarily structured like that of mammals. There are a bit fewer bones in the ear, to put it simply. The bone that's present in the ear of dinosaurs doesn't really allow them to pick up all the high-frequency sounds. However, it's very good at detecting low-frequency sounds. And so it has been suggested that the vocal range of dinosaurs would be mostly in quite low frequencies, even in frequencies that we wouldn't be able to hear. And actually, that seems pretty consistent with what we know about the animals most closely related to dinosaurs today. So that would be crocodiles and birds, which are the modern-day dinosaurs. And when we look, for example, at crocodiles and some large birds, we see animals that produce sounds called closed-mouth sounds. Well, actually, those sounds are really very rough, very deep, very muffled, but you can still hear them. So, well, maybe our dinosaurs could have produced similar sounds to communicate with each other while staying discreet. Leandra Ray asks us if dinosaurs were mesothermic. That's a very specific question. In nature today, we have what are called endothermic metabolisms and ectothermic metabolisms, and so that corresponds to the mechanism of heat production in these animals. Historically, we believe dinosaurs were cold-blooded animals, so ectothermic. It has been shown that, in fact, they were actually warm-blooded animals, endothermic, with metabolic rates closer to those of modern mammals and even birds. But despite all that, it's true that some research teams have found metabolic rates that were a bit lower than today's endotherms. It has been proposed to create an intermediate category called mesotherms, meaning animals that fall between the two. So it's not that they're capable of doing both, but really that they're, for example, closer to endothermy, but with possibilities for greater variation in body temperature that are, for example, more tolerable. This hypothesis was actually proposed not that long ago. So it's still, let's say, being challenged by other scientific teams who study dinosaur metabolism a bit more deeply than I do anyway. Despite everything, let's say that the current assessment is that this hypothesis hasn't been completely rejected, but it's not as solid as it seemed at first, so it's not really conclusive yet. For now, it's safer to stick with the most widely accepted, robust, and demonstrative hypothesis, that dinosaurs were endothermic, but studies on dinosaur mesothermy are still ongoing. So it's true that I think I can directly include the next question, which was asked by Anderson Alain, who asks us what kind of metabolism the giants of the Mesozoic had in order to live at that time. And so it's true that this is somewhat related to that. In the end, we realize that for animals that are much larger in size, it becomes an even greater challenge to produce their own body heat, because it simply involves issues, even just with digestion. They would have to ingest a huge amount of food to be able to produce that, and then metabolize it in order to generate enough heat to live, simply to move around and carry out basic functions. It's true that the giants of the Mesozoic, like the sauropods for example, which could weigh up to 50 tons according to the most conservative estimates, raise questions about their metabolism. We're not yet able to answer those questions. We're making progress, we're learning more about how these animals breathed, how they transported blood from their head all the way to their tail. Sometimes they could be 30 meters long, that's quite a distance to cover. We know they had special adaptations, but we're still pursuing research to understand how they overcame this challenge. Chena Kiryu33 asks us, how many species have been found up to today? We have a tool called the Paleontology database, or Paleobiology database, I can't remember exactly, which allows us to catalog all the species discoveries that have been made for really all extinct organisms. So in it, there's a dinosaur category. We can see where all the fossil sites are located on Earth, etc. It's really super interesting. As of December 2024, the count was at 1,380 and some species. It's also very interesting to see that we've had a lot more species that were discovered and then invalidated than discoveries of species that are still valid. So actually, it seems to me that almost 4,000 species have been described for dinosaurs, and more than 2,000 of them have been invalidated afterwards. The next question from Noel Malpias: can you estimate the average dinosaur population in each period of evolution? Well, yes and no. Let's say it's a major question to really understand the diversity of dinosaurs in each period of the Mesozoic, especially around the major transitions. So the transitions between the Triassic and Jurassic, which is considered a biological crisis, and the transition between the Jurassic and Cretaceous, which in that case was also considered a biological crisis. We have increasing evidence that this isn't always true. Anyway, that's another topic. It's essential to estimate these animals' diversity during pivotal periods. If I answer yes and no, it's because we actually have good statistical representation of these animals. As we saw earlier, there are many known species and sites. We can, for example, compare the number of unique species in each major family discovered on either side of these crises. But we will always be subject to a significant bias in the fossil record, which is that some periods are better fossilized than others. There can also be periods that are destroyed. There are periods when the sea level, for example, will recede, and so it will erode certain deposits, and that is a total loss in terms of fossil diversity. There are also places where there are potentially dinosaurs that are fossilized, but they are not necessarily accessible and often correspond to periods that are not very well known. We also have statistical biases and use various methods to address them. So it ranges from fairly simple interpolations to artificial intelligence techniques that allow us to make estimates, but overall they don't always converge. So there's actually a lot of debate about that. That's why I say yes and no. We can get an idea, but we know there are some periods that are a bit misleading. That's especially the case with the end of the Cretaceous, really the moment when the dinosaurs disappeared. There are debates saying that dinosaurs were already declining in terms of diversity before the meteorite impact, basically. But in reality, we realize that this period is very poorly sampled on a global scale. It's mostly known from North American sites. So there's a bias in terms of estimating the diversity of these animals. Yes, Meziani asks us, did all the dinosaurs go extinct? Well, no. Right now we are surrounded by 10,000 species of dinosaurs, which are birds. That's a discovery that is now widely accepted in the scientific community. We really have a lot of evidence showing that birds are dinosaurs, and that's not something that's questioned anymore. It's even something we use to make a lot of inferences. I've already done it several times during this interview regarding extinct dinosaurs. Most non-avian dinosaurs, meaning dinosaurs other than birds, disappeared 66 million years ago, following the meteorite impact and increased volcanic activity. Also, we still have birds that survived this crisis and diversified to the point where there are now more than 10,000 species today. Question from Gwen Cosette, who asks us, could we have coexisted with some dinosaurs? It's true that I love this question. It really sparks the imagination. But in reality, when we zoom out a bit, we realize that we already do, since birds, once again, are dinosaurs and they surround us, and in fact, we've even domesticated some of them. When you look, for example, yes, chickens, geese, those are dinosaurs that we've managed to domesticate to get a certain form from them. So sometimes for exploitation, it's also true some models let us have a more reciprocal relationship with these animals. And so we could totally, I imagine, suppose that if some non-avian dinosaur still existed today, we could have tried to develop this kind of relationship with them. And why not find agricultural or other uses for them while maintaining a respectful relationship with them? So I don't have much trouble imagining that. But of course, it's true that if we imagine super dangerous dinosaurs in large numbers and all, well, obviously it would be a bit more complicated. But in any case, starting from a model we know, well, I think it's not hard to imagine at all. And it's even more fun to imagine that we could have a little dinosaur as a pet, for example, at home. So now, for the question from Jerome and Tegra, how did their extinction happen? So the extinction of non-avian dinosaurs happened 66 million years ago at the end of the Cretaceous. Basically, at that time, we have evidence of the impact of a very large meteorite that is believed to have fallen in what we now call the Gulf of Mexico, in the southern part of that Gulf, around the Yucatan Peninsula. And when this meteorite fell, it raised a cloud of dust on a planetary scale. And we can prove this because in the rocks, we find a thin mineral layer that corresponds exactly to the fall of this meteorite. And this can be found on a planetary scale, really everywhere. So we know that this meteorite fell at the same time as the extinction of the dinosaurs, and there is evidence showing that it triggered a chain of catastrophic events that can fully explain a major biological crisis. So basically, not necessarily on a local scale, there's the shock, the energy from the impact, there are fires, basically anything you can imagine, but then the actual lifting of this dust cloud plus the ashes, the fires will cause what's called an impact winter. And so actually the ecosystem becomes unbalanced after the fall, after the death of the plants, in fact. And so the entire food chain collapses, actually. Unfortunately, that's how most of the dinosaurs disappeared. So that's the hypothesis that's most often put forward. But it's true there's something else, actually something huge happening during this period. It's called the Deccan Traps, and so actually that's an intense volcanic activity that was happening in India at the same time. Here we're discussing lava deposits 2 kilometers thick, covering an area the size of France. So really a very significant and very active volcanism over a fairly long period, which could also potentially have played a role, maybe overlapping with the meteorite impact. And so very often we have scientific articles that lean a bit in favor of one hypothesis or the other. I think it's more a matter of relative importance. Clearly the meteorite had a significant impact, and in this case we have studies that more or less put into perspective the importance of the intense volcanism of that time. So there you have it, we have this extinction, and I think after that we can immediately move on to Sarah's question. Urs 60 Ra, we're at the heart of scientific inquiry. Why did some species survive and not others? And here really it's this somewhat differential aspect of extinctions. Why did some species make it through, like birds for example, and why did others disappear? Well, honestly, we still don't have any conclusive evidence to answer that question. It's the same, a bit like the question of size in dinosaurs. Sometimes we have single factors that are put forward. So for example, there was this hypothesis that birds had a beak that allowed them to access certain things. Foods that could have survived this trophic collapse after the extinction, like nuts, they could have cracked small things that would have survived. But actually, that's not a hypothesis that has been tested, and we really can't put it forward. It's just very strange to see that, for example, flying reptiles like birds made it through the crisis, while flying reptiles that aren't dinosaurs like pterosaurs went extinct. So really, we don't have an answer yet for this differential aspect, and it's a scientific question that's being fully explored. And then for Renaud Vald's final question, given their weight, how did Diplodocus mate? Well, that's a question, again, that really intrigues scientists, but honestly, the problem is that we don't really have any fossil evidence to answer this question. I don't know how else to put it. We really don't have any breakthroughs or clues to study the act of mating in dinosaurs. As I was saying before, by making close comparisons, we might be able to infer that Diplodocus, animals that weighed tens of tons, would have had a particular method of mating without putting themselves in danger. That seems obvious. So then, some people have suggested, for example, that these animals might have gone into the water to counteract the effects of gravity a bit, to lighten themselves. Honestly, that hasn't been tested. Besides, that kind of fits with the old idea of a slow, cold-blooded animal living in the water, and that's really not the image we have today. So honestly, we don't have any evidence supporting that. The questions are still open, it's the same. It's pretty hard to imagine stegosaurs, for example, animals with plates and spikes on their backs mating. You really wonder how they managed it, if maybe they turned a bit on their sides. In any case, I don't think they would have climbed on top of each other, as you might simply imagine. Still, it's true that when you look at nature today, for example, when you see how modern birds do it, birds have a cloaca, which is a single organ used for both excretion and reproduction. Basically, there are several methods they can use, including making contact kind of back to back like this. So that's something we could maybe, why not imagine as a strategy that dinosaurs might have used? But that's it, we can only infer without really being able to take the analysis any further, so I can't go any further than that.
No, I'm just saying that life always finds a way.